So we decided to do an experiment that proves centripetal force exists.
Wait, centrifugal force?
No, centripetal force.
Wait, what's centripetal force? What is that?
Centripetal force is the acceleration of an object in a uniform circular motion, which is always directed toward the center of a circle.
Alright. So like, this is a race car and it's going around the track. This is the centripetal force. So that's going towards the center. But the car's velocity is going this way. So the centripetal force is what keeps it on the track. Alright, I get it. Thanks for clarifying that for me. Sorry about that.
By using a contraption that looks similar to this, with a weight tied to one end of a string, a rotating tennis ball tied to the other, strung through a tube, we'll show that the rotating tennis ball can maintain the height of the weight just 5 centimeters from the bottom of the tube.
Yeah, and in order to keep the weight at a constant height, the centripetal force of the rotating object, in our case a tennis ball, plus the weight has to equal the weight of the weight at the bottom of the string.
That's right, because the string doesn't stretch, break, or shrink, so that the radius of the tennis ball and the tube will increase as the height of the weight on the bottom increases.
Alright, so we got all this information, all the measurements. Are you going to be able to figure out what velocity we need to spin this tennis ball at to keep the weight at a constant height? Constant height from the bottom of the tube, right there, just like that. Will you be able to figure that out? What velocity are we going to need?
I can try.
You got an answer, but it was kind of like super speed, so can you walk those of us who are a little bit slower through the process?
Okay. Alright, so I started with Newton's second law, force equals mass times acceleration. So because the string doesn't stretch or break or anything like that, we know that the mass of the ball times gravity plus the mass of the ball times the centripetal acceleration has to equal the mass times gravity of the weight because it's connected.
Yeah.
So I took all those numbers together and we were looking for the centripetal acceleration because we know everything else, and we found that to be 50.2 meters per second squared. So that means you're spinning it and the ball's traveling 50.2 meters per second squared around in a circle. So the next thing we're trying to find is the speed, because that's what we're looking for altogether.
Okay.
So the equation for...
Oh, so you have to find the distance that it goes, right?
Yeah.
In a circle, which would be the circumference.
Yeah, and
So,
we need the radius, right, for the equation. Acceleration equals velocity squared over the radius. So to find the radius, we took the length of the string minus the length of the pole and the height that we're holding the weight at constantly, and came up with 49 centimeters, which is the same as 0.49 meters.
Yeah, you got to change that into meters, otherwise it's going to have everything up.
Right. Okay, so back to the acceleration equals velocity squared over the radius. We have the acceleration, which is 50.2 meters per second squared from the previous equation.
Yes.
We have the radius, 0.49 meters. So we found the velocity from that, 4.96 meters per second.
Okay.
And the velocity for a rotating object has the period in it. And so 2 pi r is the period. And so we have velocity equals 2 pi r over t.
So period is the same thing as circumference, right?
Yeah.
Okay.
So
So
velocity.
you divide the distance that it travels by the time to get the Oh yeah, we need to get the time, so we have to, yes.
Right, so we took velocity and, okay, velocity equals 2 pi times 0.49 meters, which is the radius, over time, and we found the time for one rotation is 0.62 seconds. Now what we're going to do is we're going to actually take this experiment into real life, time it out, and see how close we got to this theoretical number.
Human error. Hopefully it's not there.
Yeah, hopefully. Let's try it. We're going to weigh our tennis ball first.
Oh no. Wait. Redo. Here we go. Yes.
It appears to be 40
40
grams.
grams.
A 250 gram weight straight from a letter weighing scale.
So you want to check it out and see if they had it right back in the day? I think we better.
Nope, it's 245. As you can see, the weight is much heavier than the tennis ball. So here's our contraption. We have a pole, we have a ball at one end connected to a string with a weight on the other hand. And if our predictions are correct, then the centripetal force of the ball spinning plus the force of gravity on the ball should hold the weight at a constant height.
So just to show that this ball's centrifugal force can raise the weight, let's start spinning it. As you can see, the radius is getting larger and the weight's raising. But for this experiment, we'll try to keep the weight at a 5 centimeter height, and then the time it takes for 10 rotations to get an average time for one rotation.
Alright, let's do it. Alright, don't mess this up, Andrew.
Definitely not.
I got a burrito waiting for me.
That's when to go.
Alright, ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Alright, I got 6.226.
I got 6.228. I got 6.32. I got 6.40.
Trial 2. Trial 2. You guys ready?
Yeah. Yep. Go.
Ready, set, go. 1, 2, 3. Oh, fuck. Got caught.
Just go do it again.
Alright, ready for trial 2.
Trial 2. Take 2.
You ready to go? Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Trial number 3.
Trial number 3. You guys ready?
Yep. Yeah.
Alright, here we go. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Alright, Amy, it's back to the drawing board. Now that we did all our trials, we got our numbers, and we get to see how well we actually did with the spinning and the checking the times with the cell phones and this and that. So we got our times for our first trial. Average together, 6.294. Wow, that's really close. Interesting.
Not bad.
Very, very close. You went ahead and calculated the percent error for us. It was only 1.5. I'd say kudos to us for being great scientists. Trial number 2 came to 6.017. That's not quite as bad or as good as this one, but it's still really close. On that one we got a 3.04 error, which I think that's good. I mean,
It's pretty good.
I think it's damn good. Trial number 3. Wow, 6.244. That's better than this one. So 0.7 error. I mean,
Almost
come
perfect.
on,
Almost perfect.
we're incredible.
We're incredible.
A's for sure. A pluses.
And in order to calculate that percent error, what I did was I took the theoretical time, 6.2 seconds, subtracted that by the actual time we got, and for the first trial, 6.294 seconds, divided by the theoretical 6.2, multiply that by 100 for 1.5. Did that for trial 2 and 3 also.
Sir.